Alrighty, so back to chapter 4. A minimal tree. Alright. Minimal tree. So function is minimal tree. We have insert mode on, don't we? And I'm not sure about this yet, but alright, minimal tree. Given a sorted, increasing order array with unique integer elements. Okay, so unique integer elements sorted. Write an algorithm to create a binary search tree with minimal height. Okay, so I think this is just... It's actually a little while ago that I read this, but... Okay, alright, so yeah, read it again. So actually I'll just write it down, since it's so small. Minimal, why do I have so much trouble with that word? Given a sorted, increasing order array with unique integer elements. E-L-E-M-E-N-T-S. What is wrong with that word? Oh, is this it? Okay. Write an algorithm to create a binary search tree with minimal height. Alright. Okay. So we probably don't need... So the minimal tree is just going to take an array, right? Or a vector of integers. Right? And it's going to return a tree of some sort, you know? So... yeah, so... I just like to do this, I don't know why. Or at least today I do. So for the minimal array, it should return the... Let's think about some tests. For the empty array, it should return the empty tree. So I guess to start with, what are we defining? What does an array look like, and what does a tree look like? Well, the array is just a sequence of integers, and the tree is a map with a children attribute. Or, I mean, since it's a binary tree, so maybe we should just have a left and a right. No, let's have children. And the children should be empty, right? Match. What's happening here? Let's see. You know, yeah, I don't think that's necessary. It's just the assumption is always the last argument is the result, and the first few things are the inputs. I really something about this just isn't great. Not call minimal tree with one argument. I guess you're right, but we got to do something about that. Okay. Okay. So how would this work? Well, let's figure out how we build a minimal tree first, which I think they may have told us. So it was several days ago that I read this chapter, so I just kind of forgot. Okay, so binary tree, I'm just reading a section. Binary tree versus binary search tree. A binary tree is a tree. A binary search tree is a binary tree in which every node fits a specific ordering property. All left descendants are less than or equal to n, are less than equal to, are less than all right descendants. Let me read that again. All left descendants are less than or equal to n, are less than all right descendants. Okay. So just write down that definition in here. Well, let's first just actually write convert sequence of integers to binary search tree. Also just define what a binary search tree is. Okay. I'm going to just define it as a binary search tree is a binary tree in which every node fits a specific ordering property. Descendants I guess it doesn't know that word. Less than or equal to n. Less than all. Descendants. Okay. Okay. So that's cool. We need to build it though. And let me just get the distinction between balanced versus unbalanced minimal. So I don't think they've mentioned the word minimal here. But I think a balanced tree is minimal. Okay, so if I assume that a So is this just a in order to create a binary search tree with minimal height? To create a binary search tree with minimal height. So BST is just a tree. I think I'm missing a section here. Maybe I should stop and read some of this. Yeah, I don't see in the book the word minimal. But is a Is this just asking for a min heap? Is that the same thing? I'm not really clear. I mean, a min heap has the property to complete binary tree, where each node is smaller than its children. Well, that can't be true then, right? Each node can't be smaller than its children and also be a minimal or a binary search tree with minimal height. So how would you actually put nodes into a tree in order to ensure that all nodes to the left are smaller than all nodes to the right? And what would that mean? What would that tree look like? Well, I guess it would mean things like if I had 1, 2, 3, 1, right? Then I would have a value of 1 and a children. That's actually kind of weird, isn't it? I mean, I guess you don't even really have a node, do you? Now that I think about it. So, about 1, 2. Well, you have a value of 1, and you've got a value of, well, no, this would actually be a value of 1, and this would be a value of 2, I think. Is what you'd end up with. What about 1, 2, 3? Same thing, except you have a value of 1 on the left and a value of 3 on the right. So our rule here is that you don't evidently include children if you don't have any children. So that's something. What about 1, 2, 3, 4? I guess it kind of depends on how you implement things. But I guess if we're going to try to fill things in from the bottom up, right, we'd have a value of, well, what went to 1, 2, 3, 4? I mean, eventually the tree has to be rebalanced, right? That's really complicated. I mean, am I going to invent this on my own? It seems a little hard to believe. Something weird. That seems a bit unlikely. If I just build a balanced have read it, but I'm just gonna fold. Okay. I mean, I guess because we have a sorted array, we don't have to process it one item at a time. Okay, maybe the fact that it's a sorted array is supposed to be a big help to us because we don't actually have to figure out how to balance this binary tree ourselves. Instead, we can just find the midpoint, take that as the value, and build the children recursively. Okay. Alright, so we got an array. I need to find not really clear, but I'm just going to take a VS. And what it's going to do is it's going to find the midpoint of VS. And the midpoint is generally going to be the center, but it's going to lean towards the right in the event of even numbers. So, gosh, I feel like we saw something for this a while ago. Oh, it was with that linked list thing where you can have two. But yeah, I think that's silly. Let's just say that, the midpoint will be the VS count. Alright, so like, let's say you have 4, right? The midpoint will be 2. And we're going to round up. I think so, yeah, we're going to round up. So if the length is 4, your midpoint is 2. Actually, you've already rounded up, I think. So you're saying start at position 2. And so our position 2 is the thing you're going to put into the node itself, and sequence containing 3 is what you're going to pass to the right, and sequence containing well, sorry. So we're basically saying if you're passing 0 or 1, 2, 3, 4, midpoint is going to be 2. So you're going to put 3 into your node, and you're going to pass 4 to your right, and you're going to pass 1 and 2 to your left. Okay. So if your midpoint is that, so 4 becomes 2, and 5 becomes, I want it to also be 2. So let's actually pull the right mathematical thing. It's like quote remainder, quote closure. I think that's what we want. Quotient of dividing numerator by denominator. 10, 3, you can take 3 of those out of 10. 11, 3, you can take 3 of those. So you have 5, 2, you can still only take 2 of them. So I think it's quote, yeah, of 2 is what we want. And so now we're saying, if you pass in 5, we're saying 0 and 1 go to the left, and, 1 and 2, 1, 2, 3, 4, 5, we're saying 1 and 2 go to the left, 3 is the node, and 4 and 5 are the children. Okay. Midpoint of VS, okay. And then, so what we're going to do is just recursively define the node as node is equal to nth of VS I. Children we'll see this in a second here, but I guess there's a distinction between when you have children and when you don't. So and you should only not have children if what about the case? So there's a 1, 2, and 3 case that is as an I am a node of size 1, which means just return yourself, node of VS, right? There's I'm a node of size 2, which means split yourself down the middle. Ooh, what does it mean? No, that's not what it means. Actually, it means take 2. If you're 1 and 2, your value is 2 and your left child is 1. And then there's so actually, I do actually think that you maybe should handle the case of the empty VS, right? Because that should just return nil. That should return nil, right? So because we know this occurred, we know nobody who's coming by here is actually at least has one element, right? This handles the case of 1 element or 2 elements or 3 elements. But when we're saying well, I mean, we're not really saying anything here. We're saying well, if we're going to do that, we might as well just put it in here. All right, we're gonna take VS. We're gonna subvec on 0 to I. That is not inclusive on VS for this guy, and we're going to call minimal tree recursively on that. Similarly, for the other child, we're going to subvec on the increment of I, right? We're going to call minimal tree recursive. Now, either of these could have ended up passing. What could this subvec be? Well, it could be 0 elements, 1 element, or 2 or more elements. 0, 1, 2, or 3 elements. Do each of those need to be handled separately? Well, 1, 2, and 3 should all be able to get a midpoint. They should all be able to get this, which should just be, for the case of 1, both of these will be the empty vector. Right? Yeah. Or, I'm not clear if you can subvec on, let's see. You subvec on the empty vector starting in position 1. No, you can't. Okay. So, I don't know. I don't like handling these little. Okay, minimal tree. When not empty VS. Is that really necessary? Well, yeah, you're just not going to be able to calculate the midpoint. Well, you're going to get the 0. Count is 0. Divide by 2 is still 0. It's going to say that you should be splitting at position 0, but you're not really because you have no element. So you really should just return nil, I think. let's just explore. What if we just said is VS empty? Okay, return no. Is VS the count of VS 1? Okay, then just return the node at I said no, but just return a node with value of 0, right? Is the count of VS 2 or more? Let's just do all 3 of them, yeah. And actually, if we're gonna do this, we might as well say, right? So we're just gonna keep saying the same thing. So if it's 0, return nil. If it's 1, return this. If it's 2, it's a bit of a weird one, but return value of let's just see what happens here. Int of VS, I want you to take 1 as your value, and I want you to go into your children and pass in just the first one. You don't have to do the math anymore because we just know what you are. So it's just minimal tree. We want to get the nth of VS of 0. Which is also just the first, really. And I meant the first VS. Alright. And then finally, we got an else, or no, we have a default, which is going to be this whole node. Which I think is just going to be this entire bit of logic. We now know that you definitely have 3 or more nodes, which means you're going to have a midpoint. We're going to take your midpoint as the node. We're going to subvec on the children from 0 to I, right? 0 to your midpoint, which does not include your midpoint. And we're going to recursively call and subvec on the midpoint plus 1, starting at that position, the minimal tree. Feels like I do this so often that there should be a function that just makes this a little easier. That just like always, you know, okay, so I got a subsequence. I need to return 3 things. I need the thing previous to this index position. I need the thing at this index position. Sorry, the sequence previous to this index position, the value at this index position, and the sequence post this index position. But it seems like I should just have a function for that, you know, because it's something I do quite often, or at least it feels like at least the second or third time I've done this. Okay, but anyway, that's the minimal tree. And then so there really isn't. I think it is just a recursive function. I don't think there's anything to, like, I don't think we need to set up anything before we do the first one. It really does just take VS's and recurses on itself. And let's see what happens. Could not resolve symbol minimal tree. Well, yes, you're right. I hate this. We got it. Alright. I don't know what to do about it personally, but Wrong number of args for past the closure course subvec. Okay. You're right. We are threading VS. We don't need it. Count not supported on this type long. Where would that be happening? I think there's only one. It's in 4. Alright, so let's just get those. Let's get the silly ones out of the way. Okay, so that works. This should hit the first case, right? Yeah. This should hit the second case. But it doesn't. So 2 says take the value. Take the value 1. 2 says take the value at 1 and take the value at take the value at 1. What could be going wrong here? Minimal tree. Oh, I see. It does need to be a sequence that you pass to this guy. So it's technically just the top of VS. Okay. Move beyond that. 1, 2, 3. Okay, let's see what we got. Alright, so I'm claiming that you need to have children of 1 and 3 and a value of 2. But you're saying what actually happened is we had children of 1 and 3. That looks similar, and a value of 2. Oh wait, that's the same thing. Children, value 1, value 3. Oh, I said a node of 2. That's not right. It should be value of 2. Okay. And 1, 2, 3, 4. So I think what I'm claiming here is that you should have a value of. So what is the midpoint on this one? I think the midpoint is now 3, right? According to what we want. This guy should have a value of 2. His children nodes need to be less than him though, so should have a value of 1. Oops. Should be a map. And the last node should have a value of 4. Alright, that looks kind of good. Let's just think about 5. Alright, 5 we definitely now do have a midpoint of 3. children should have a value of 1. No, children. So 1 and 2 is passed to it. Does. Okay, children has a value of 1 and 2. So that means I think this is identical, but this is now closer to that, right? 1, 2, 3. This guy, no, this isn't minimal anymore, is it? I'm not quite clear. It's not a complete binary tree. What does minimal mean? Given a sorted increasing order array with unique integer, write an algorithm to create a binary search tree with minimal height. So I think it does have minimal height, but what is the definition of a binary search? I mean, the only technical definition of a binary search tree, I think, is that your descendants on your left are less than or equal to n, are less than or equal to all right descendants. This must be true for each node. Okay. Well, we got a value of 2, children value 1. Alright. But somehow I kind of feel like this guy should have... I mean, so is it a binary tree? It meets the definition. It meets the definition, I believe, of a binary tree if it does this, right? Let's think about it. 3 has 1 and 2 to its left, and 4 and 5 to its right. Right? 2 has 1 to its left and nothing to its right. 1 has no children. 4 has 5 to its left, and... oh, that's wrong, isn't it? The only way to actually do that right would be to do this at some level. Interesting. Okay. But I'm not sure whether value 5, because it could also be the case. It could also be the case. Well, then you might say what really you have here is you have 5, with 4 to its left, right? Which is, kind of makes 5 has 4 to its left and nothing to its right. But that is a balanced binary, or that is I think that is the definition of a search tree, but that is not a complete binary tree. Okay. But can I use this for search? Well, yeah, I think you can, because all you need is that all the things to the left are greater than all the things to the right. Or sorry, the things to the left are less than are equal to your node, and the things to your right are greater than or equal to your node, and that is true of this tree. It's not conventional, and then it looks... well, it's just not conventional. Or it's not complete, I guess. I don't know what's conventional, what's not conventional. So I'd agree. That's how it built it, but it would be nice if it was also a complete binary tree. But how would it need to be built to be a complete binary tree? Well, I think you'd actually have to split it along 4, right? So it'd be, and just like metaphorically, well, that was a pretty long syntax, or I should have written this a better syntax, but whatever. But it could also be that you'd make the argument that it should look like, I think value 4, node 2, children 1, and children 3, value 5, and no children, right? Huh. I think actually it has to be that way. Because without this, well, without this, I'm not clear that I'm actually minimizing the height. Although, where's the next one going to come in? The next one is going to come in under this node, right? And so rather than having just... Well, let's just see what happens. I think I just have to do them because I can't really do it in my head. 1, 2, 3, 4, 5, 6. Right. I should have written a better syntax for this. But we have no clear midpoint here, right? There's no... It's even, is what I'm saying. So 1, 2, 3 is going to be past the thing. So still 2, value 1, but now this guy also gets the value 3. Right? And 5, 6 goes to the left. So this guy becomes 6, and this guy becomes 5. Yeah. Same thing for 7, except now the midpoint is obvious. So left is unchanged, but right... getting pretty ridiculous. I should have written this. I should have just written this as a vector of vectors. As a... All right. Oops. Add program. Okay. Okay. All right. So is this the minimal height? Well, it feels like it, right? Because now we've got 7 elements that we're putting at a total height of 2, right? Is that right? 3, I mean to say. Where this is level 1, this is level 2, and this is level 3. And so I don't care how you arrange things. You know, if you can add 4 plus 2 plus 1, right? 4 plus 2 plus 1. That's the most you can stick. You can only stick up to 7 items at a level 3 binary tree. And so it seems like we are at the minimal height. It's a bit of a weird binary search tree in that it's not complete. Which I don't know what that does in terms of manipulation of the tree, right? Since there's no kind of place to start from, you don't know whether I would have put certain things. It's ambiguous where I would have inserted certain things. Well, it's not definite. I could have, specifically on the, like I was saying, on this one, right? I think you could hand 1, 2, 3 to the left side and node on 4 and B on 5. Was there ambiguity here? I don't know. Anyway, that's okay, I think. Now let's just try making this syntax a little easier to read, because this is too complicated to read, right? And so what we want to do is, so we're just going to convert vector trees to trees, right? And these should just take a VS, right? that is always going to be of the form, right? V left and right, right? And all it does is just expands into this. Value of V, well, unless it's empty, in which case it's nil. You know, I guess the nil never really, well, it did occur. But yeah, because we have these three terminal cases, these two terminal cases, we don't really have to worry about this, actually. It doesn't really occur in tree expansion. It doesn't expand into the 0th case. It only expands into the 1st and 2nd case. Or the 3rd generic case. But, so this nil, okay. Merge the value, then merge the children. Which should be made up of the so if left or right is nil, how should I do this? If you specify a left, then it should be the, let's just say when there's a left, right? Actually, let's just do the even not more obvious thing. When and there's a left and a right, right? Then just do children of vector tree to tree of left, right? And vector tree to tree of right. When there's, however, just a left, then just do children. Oh, whoops. Because it'll obviously hit both of those. Oh, let's just be dumb, alright? You know what, that is dumb, actually. When VS, then do this whole thing. And okay, so everybody's got a value, assuming they got past this point, right? And if you got a left or a right, we're going to try to call it, you know, which may return nil because you may not actually have a right. Or, actually, that's the only thing that should happen, is you should maybe not have a right. So we're going to remove the nil, then we're going to convert it into a vector. Not resolve symbol left. Ah. Okay. Now let's just see if we can convert these into something slightly more succinct. 1. Huh. Well, isn't that what we had there before? Value of 1, right? You're okay with that. Oh, well, we need to actually do the thing. Okay. Oy. Oh, it just doesn't work. Duh. Q other. Okay. It doesn't work for the first one, is what I'm asking. Oh no, not if you can please screw up here. Lines. First of all, let's check this. That doesn't work either. Why would that? Something wrong here? It just seems like it's okay. Does not work in persistent array map, but who's calling it? It's it's from okay, just to make sure, let's sort of undo that. Maybe this isn't a good idea. I kind of feel like the expected should be identical to what you see, but it is kind of hard to read in my mind. I guess we can technically be a little more permissive by saying okay. Now let's try this one. Okay, still seems to work. How about this one? Of course it's a failure, but we expect that. 2 and a thing containing 1. Okay. Yep. 2 and a thing containing 1 and 3. So this is passing in the sequence 1, the vector 1. This is passing in nil. So nil should definitely just nil out. Remove itself. Oh, does it need to convert itself into a vector? Well, yeah, it does. But 2 should, or 1 right here, should get passed here. It's going to just be a vector with the value 1. It's going to have no left or right. Do we even need this? Well, we needed a left or right, so otherwise we shouldn't have children. Yeah. Okay. Value 1, value 3. Is not supported on this type. Persistent array map. Okay, but there's definitely an issue with this. Don't know how to create iSequence from a Java Lang long. I think I see what you're saying. You're really saying this 3 is technically in its own child. So that feels wrong, right? 1 should be less than 3. Yeah, it really shouldn't be like that. Wait, is that what we said it should be? Because let's see. Should be children with 2 nodes. So I think it should actually be 2 with children of 1 and children of 3, right? There we go. Alright. Let's just look at this closely. Should be 3 with 2 nodes of... The first node has a value of 2 and a children of 1. And the second node has a value of 4 and no children. Okay. Should be 3 with a value of... First child has a value of 2 and the children of 1. The second one has a value of 5 and a children of 4. Okay. children has a value of 4, has a value of 2, a children of 1, and 3, and has a value of 6, a children of 5. Before this, we're saying everything's fine, but up to this one, we thought we did it by saying 4 has 2 children. First child, second child. The first child has a value of 2, the second child has a value of 6. The first child has 2 children, I think I did that wrong, I see, of 1 and 3, right? The second child has 1 child of a value of 5. Okay. Again, a value, or pretty much identical to this, except now we're actually going to have 6, 5, 7. Let's just see. I don't always support this, but closure align doesn't really help. That's okay. I'm not a big believer in that anyway. It is a bit hard to read considering how easy it should be to read. But yeah, I think that's a little bit better to parse, maybe. I do think maybe we can do this. I don't know if that helps. Maybe the children were better. Anyway, we did it, so whatever. Now let's go, okay, so that's it. I'm gonna now look at the hints and stuff. It's a 4-2, first hint is number 19. A minimal binary tree has about the same number of nodes on the left of each node as on the right. Let's focus on just the root for now. How would you ensure that about the same number of nodes are on the left as of the root is on the right? You could split it in two. Okay. 73 is... You can implement this by finding the ideal next element to add and repeatedly calling insert value. This will be a bit inefficient as you would have to repeatedly traverse the tree. Try recursion instead. Can you divide this problem into subproblems? Okay. Number 116. Imagine we had a create minimal tree method that returns a minimal tree for a given array, but for some strange reason it doesn't operate on the root of the tree. Could you use this operation on the root of the tree? Could you write the base case of the function? Great, then that's basically the entire function. Alright, so that's not a huge amount of interesting stuff there. But let's look at page 242 to just look at the actual solution. To create a tree of minimal height, we need to match the number of nodes in the left subtree to the number of nodes in the right subtree as much as possible. This means that we want the root to be the middle of the array. Since this would mean that half the elements would be less than the root and half would be greater than it. We should proceed by constructing our tree in a similar fashion. Left subtree. One way to implement this is to use a simple root insert node method.
recurse. Huh, that's funny. So the way they do it is they build the left and the right node first, and then they recurse into the left and the right node. So basically, their function. Now let's see. All they take is an array and a start and an end. Okay, that's an interesting thought. So yeah, they just take an array and a start index and an end index. I mean, we don't do that because we can just subvec, which is equivalent. But it's just a single data structure rather than a data structure in 2 arguments. For each recursion, they create the node first, then they set the left and the right to the recursed value with the, and they return -1. Or sorry, then they return n ultimately. Okay, I guess it's pretty much the same thing, I think.
One thing I would like to make before we close this off is just write the function to take an element out, give me the things before and the things after, right? What should we call this? Like, let's call it... what does the word bisect really mean? Yeah, so I want to do more than divide into 2 equal parts because I want to I don't have a great word for it, but let's look at synonyms maybe, or things that are like that maybe. Furcate. I like that word. How about just separate? I don't think it's a Clojure core word at all. And these articles are just not great, I think. So, hello. Looking for my Clojure cheat sheet. Is there a separate? I don't think there is. Of course, I need to remember how to spell it correctly. Separate. A-R-A. Alright, so since there is none, let's just call it separate. It's not the greatest name in the world, but if we can think of something better, we should do so. So VS and I, right? And I just want you to return me something that is literally the subvec of VS to I. So that does not include I. The int of I of VS. And the subvec of the increment of I on VS. Okay, just make sure that's valid code. Alright. And I'm not clear if this works with can you take the nth of so let's say I have an element with one thing in it, right? Can I take the subvec of 1? Yes, you can. Just returns the empty vector. Alright, so that's fine. Left v right, separated I, vs I. Okay. So now I feel like we can just put this stuff in a little bit more clearly. Whoops. Evidently not. How about that? Did that work? Yes. So something's wrong with our subvec of vs. Oh, I forgot to do 0 of I. 0 to I is what I meant. Okay, let's try left. Damn. What is your problem? Left subvec vs 0i, right? What is the difference? That really shouldn't be much. Subvec of vs from 0 to I. Now, why does that not work? Subvec from 0 to I of vs. Subvec of vs 0 to I. No, that's not it at all. Right? Subvec 0 to I. I just don't see the distinction here. Oh. Weird. I don't know what I was mistyping before. Alright. I think that's a little bit clearer. Then finally, a tiny little performance thing I guess we could technically do is technically these are constant values, right? So I think we can actually just do case equality count of vs. Let's see. Yeah. So now it should be constant cost too. Because previously when you did the con p equals count whatever, you know, it does the count once, but then it's got to actually linearly walk through them. Now it's going to just, it's a dispatch basically. And I think that's enough. Okay, MGS stage. Give this sort of increasing order, alright, commit. Why is this? Oh man, did I never even change the name of this thing? Okay, well. Okay, MX beard. Oh my gosh. Text is too big. I think I am gonna make it smaller. It's just too large. But okay, now XW. I'm going to change it to Chapter 4, Problem 2. This is minimal tree. CLJ. Okay. There's no reason that should start failing just because we get this, but yeah, okay. But now MGS. So we need to stage this one. We need to unstage this one. Okay. Can drop this one. Just make sure this absolutely is the right one. Yep, okay. We can drop this one. And commit. CK. Alt W. Commit. Minimal tree. Okay. Wait, why can't I just amend? That's what I did, right? Yeah, okay. Alright, whatever. I'll deal with it later. Or just forget about it and who cares? That's it. Stuff.